Hey there. Ever stop and wonder what holds, well, literally everything together? I mean, the water you drink, the chair you're sitting on, even the air you're breathing right now. It all comes down to chemical bonds, these incredible, invisible forces that build our entire world. Today, we're going to dive deep into this universe of atomic attraction and figure out the rules. So, what are these rules? It's not some big mystery or magic spell. It's actually a pretty clear set of principles that tell us exactly how atoms are going to interact with each other. Let's get into it and uncover the rules of attraction that run the atomic world. All right, first things first, to understand how atoms bond, we really need to understand why they do it. I mean, why don't they just float around all by themselves? And the answer comes down to one simple, powerful drive: a constant search for stability. Okay, so think of it like this. Atoms are at a big cosmic party. The noble gases, helium, neon, argon, they're the cool kids. They've got a full outer shell of electrons, which basically means they're perfectly stable and content. They don't need anybody. But most other atoms, they show up with an incomplete shell, and that makes them unstable. Kind of antsy. So their one and only goal is to find other atoms to interact with, to gain, lose, or share electrons, so they can get that perfect, stable, noble gas set up. So how do they pull this off? Well, they've got two main strategies. On one side, you've got ionic bonding. This is a total giveaway. One atom literally hands off an electron to another. This creates these charged particles we call ions, a positive one and a negative one, and boom, opposites attract. Then on the other side, you have covalent bonding. This is more of a partnership. Two atoms agree to share electrons, working together to form stable molecules. It's really the difference between giving someone a gift and sharing a meal together. Okay, so we know atoms connect to each other. But here's the thing. These connections aren't just flat lines like you draw on a piece of paper. Molecules have real three-dimensional shapes, and that geometry is absolutely critical. It determines pretty much everything about how they act in the real world. So how do we predict these shapes? Our go-to tool is something called the valence shell electron pair repulsion model, or VSEPR for short. I know it sounds super complicated, but the idea behind it is actually really simple. The electron pairs in an atom's outer shell are all negatively charged, right? So naturally, they push each other away. VSPR theory just says that these electron pairs will arrange themselves in 3D space to be as far apart from each other as possible. It's all about giving each other some personal space. Now here's where it gets interesting. Not all of these electron pairs are created equal. You have bonding pairs, or BP, that are shared between two atoms in a bond, and then you have lone pairs, LP, that belong to just one atom. And these lone pairs, they're a little more selfish. They take up more room and they push away other electron pairs much more strongly. As you can see here, the repulsion between two lone pairs is the strongest of all. This little pecking order is what fine-tunes the exact angles and the final shape of the molecule. So VSEPR is fantastic for predicting the overall shape, but it doesn't really tell us how the bonds themselves are actually formed. To do that, we have to zoom in way in and see how the electron orbitals of different atoms actually start to interact. And this brings us to valence bond theory. This theory asks us to picture an atom's orbitals not as neat little circles, but as fuzzy clouds showing where you're likely to find an electron. According to valence bond theory, a covalent bond forms when these electron clouds from two different atoms actually overlap in space. And in that shared space, each atom brings one electron to the table, and they pair up to create that strong, stable bond that holds them together. But there's a catch. Just smashing those basic orbitals together doesn't explain the shapes we see in a lot of common molecules. Let's take methane, or CH4. It has a perfect tetrahedral shape, with all the bonds angles at exactly 109.5 degrees. To explain this, we need a new concept: hybridization. Think of it like an atom is a chef, mixing ingredients. A carbon atom takes its standard orbitals, one s orbital and three p orbitals, and basically throws them in a blender. It mixes them up to create four brand new identical sp3 hybrid orbitals. And these new orbitals are perfectly arranged to point to the corners of a tetrahedron, ready to form perfect bonds. And once these bonds are formed, we can describe them with a few key characteristics. Bond length, that's just the sweet spot, the most stable distance between two atoms. Bond angle is what we just talked about. It defines the molecule's shape. Bond enthalpy is all about strength. It's how much energy you'd have to pump in to break the bond. Bond order is simple. It tells you if it's a single, double, or triple bond. And finally, bond polarity tells us how fairly those electrons are actually being shared.
So far, we've kind of been treating electrons as if they belong to a specific bond between just two atoms. But what if we zoom out again and look at the molecule as one big picture? That takes us to our most powerful model, and to a very important special case. This is where molecular orbital theory comes in, and it's kind of the final boss of bonding theories. Instead of just overlapping, this theory says that the atomic orbitals combine to create brand new things called molecular orbitals that cover the entire molecule. Suddenly, electrons aren't just stuck between two atoms anymore. They can be delocalized, belonging to the molecule as a whole. This is the only theory that can correctly explain why, for example, an oxygen molecule is magnetic, something the other models just can't predict. And we absolutely have to talk about a very special player in this game, the hydrogen bond. Now, this isn't a true covalent bond, okay? Electrons aren't being shared. It's more of a powerful attraction between molecules. You can think of it like the superglue of chemistry. It's what holds water molecules together and gives water all its weird and wonderful properties. It's also the force that literally zips the two strands of your DNA together. It might be weaker than a covalent bond, but honestly, life as we know it couldn't exist without it. Whew. So we've covered a lot of different theories, and you might be thinking, okay, so which one is the right one? Well, the best way to think about it is that they're all part of a chemist's toolkit, and you use a different tool for a different job. So let's recap that toolkit real quick. Lewis theory? That's your quick sketch on a napkin. It's great for counting electrons and figuring out the basic connections. VSEPR theory is like your 3D modeling software. It lets you predict the actual shape. Valence bond theory is your microscope. It lets you zoom in and see how those orbitals overlap to form the bonds. And finally, molecular orbital theory is like a supercomputer, giving you the most complete, powerful picture of how electrons behave across the whole molecule. They don't compete with each other, they're just different lenses for looking at the same amazing reality. So, from an atom's simple desire for a stable life to the complex dance of molecular orbitals, these are the fundamental rules that literally build our entire universe. And they give us the power not just to understand the world, but to design and create brand new things. So, I'll leave you with this. Now that you know the rules of attraction, what molecule would you build?